Good morning, everybody. Hope you're all healthy and safe. Let us continue with our section 4.1 on the Laplace transform. So, in the previous lecture, we had seen the definition of Laplace transform, and we had also seen how we can determine the Laplace transform of some basic functions. We had just showed it by the examples. So now, as I had mentioned in the first lecture, the Laplace transform, just like integration and differentiation, it is also linear. Okay, that is we are familiar with the linearity of the integration and differentiation. So in similar way, we can say that the Laplace transform, they also are linears. So that is del of alpha into f of t plus beta into g of t is nothing but alpha into script L of f of t plus beta into script L of g of t. So that is, you can also write it as alpha into capital F of s. So like I had mentioned earlier, after the transform, after applying Laplace transformation, we get the function in terms of s. Okay, so that is alpha into capital F of s plus beta into capital G of s. So this is the linearity definition which we are all familiar with. So what we'll be doing is, in this lecture or in this section, we shall be doing some formulas, some problems which will use this property of the Laplace transform. So let's see, if you are given to us, or if you are asked to find, we know that the Laplace transform of 1 and Laplace transform of the polynomial function t. So we can find what is the Laplace transform of 1 plus 5 into t. So by linearity of Laplace transform, this is nothing but the Laplace transform of 1 plus 5 into the Laplace transform of t, right? So Laplace transform of 1 is 1 by s plus 5 into 1 by s square. So altogether this will be 5 plus s by s square. So this will be our corresponding Laplace transform of 1 plus 5t. So this is true for all cases where s is, or this is defined where s is greater than 0, because otherwise this is there is no problem in 1 and t. We had seen that in the determining the Laplace transform of e raised to minus 3, it is defined only for s is greater than minus 3. So that is because of the fact that the integral should exist. So similarly, we know there is just one more thing we shall just see roughly. We know the Laplace transform of e raised to minus e raised to 6t. So this is similar to e raised to minus 3t. So this will be nothing but what will be the corresponding value? It will be equal to 1 by s minus 6. Okay. So you can just verify it if you want to, and this is valid for all s greater than 6. We had done the case e raised to minus 3t in the previous lecture, so here we'll have s is greater than 6. Also, what is the Laplace transform of sine of 2t? We had done this, and we know that it exists, and this value was correspondingly 2 by s square plus 4, and this was valid for all s greater than 0. So since this Laplace transform is valid for all s greater than 0, for s greater than 6 also it's valid. So with the help of these two values, we can determine the Laplace transform of the function, say 2 into e raised to 6t minus 15 sine 2t. What will be the value? By linearity, this will be 2 into Laplace transform of e raised to 6t minus 15 into Laplace transform of sine 2t. So this is nothing but 2 into 1 by s minus 6 minus 15 into 2 by s square plus 4, right? So this value will be nothing but, I'm not simplifying it further, 2 into 2 divided by s minus x minus 30 divided by s square plus 4. Okay, and we shall see just one more example, and I hope you guys will be clear with the concept of linearity. We can find the linear Laplace transform of e raised to minus 3t plus 5t plus 8. What will this value be? This is nothing but 10 into linear transform of e raised to minus 3t plus 5 into linear transform of t plus 8 into linear transform of 1. Now this value is 10 into 1 by s plus 3 plus 5 into 1 by s square plus 8 into 1 by s. So this is 10 by s plus 3 by 5 by s square plus 8 by s. So if you want, you can simplify it further, or you can leave it as it is. So this is how we use the linearity concept of our Laplace transform. So in all these examples that we have seen, we have just used the examples examples which we have already done. So with the help of that, we just explained the concept of linearity. So now there is one more thing. It is there are as we had discussed or we had found out what are the linear transform of Laplace transform of some basic functions that we know. So corresponding to that, we have some basic some formulas which we can keep up in our memory, so that it will be easy to do the calculations. So that is the linear transform of 1 is 1 by s. Linear transform of the polynomial t raised to n is equal to n factorial by s raised to n plus 1, where n is 1, 2, 3. So with the help of the second one, we can determine the linear Laplace transform of any polynomial function. Okay, so the Laplace transform of t raised to n is nothing but n factorial by s raised to n plus 1. Then we have the Laplace transform of the exponential function e raised to a into t, where a is some constant, which is equal to 1 by s minus a. Then we have the Laplace transform of sine kt, which is equal to k by s square plus k square. And sine h, that is hyperbolic sine, the Laplace transform will become k by s square minus k square. Okay, in one case it is in normal trigonometric function it is s square plus k square, and in hyperbolic functions the denominator becomes s square minus k square. And in case of cos, the numerator changes, that is Laplace transform of cos kt is equal to s by s square plus k square, and Laplace transform of cos hkt is equal to s by s square minus k square. So these are the Laplace transform of some very basic functions which whose linear combinations can be used and found, and we can find the Laplace transform of bigger functions. So more Laplace transforms are given in the appendix of your textbooks. You can just go through it. So just we shall be doing more problems in the assignments and all to make the concept more clear. So that's it for today's session. Thank you. Stay safe, stay healthy.